The universe, that unfathomable vastness that extends beyond the confines of our understanding, is often associated with an enigmatic darkness that challenges our senses and our imagination. The inevitable question that echoes in the minds of scientists, astronomers, and philosophers is, why is the universe dark? In today's video, we will present 10 theories that try to explain the reason for the darkness in the universe. But first, if you haven't subscribed to the channel yet, subscribe and help us reach the 1,000 subscriber mark. Redshift theory and expansion of the universe. One of the main reasons for the apparent darkness of the universe is the phenomenon of redshift. Redshift occurs because the universe is constantly expanding. As galaxies move away from each other, the light emitted by them is stretched to longer wavelengths, which reduces their energy and makes it harder to detect. As a result, many distant galaxies appear fainter and redshifted, which contributes to the darkness of space. This theory has its roots in the observations made by astronomer Edwin Hubble in the early 20th century and was one of the first concrete evidences that the universe is constantly evolving. Redshift is a phenomenon observed when light from a distant source is shifted to the red spectrum, meaning the light becomes longer as the source moves away from the observer. This displacement occurs due to the expansion of the space between the light source and the observer. The greater the distance between the observer and the source, the greater the observed redshift. The theory of redshift and expansion of the universe is based on a few key ideas. Hubble's law. Edwin Hubble formulated an empirical relationship between the speed at which galaxies move away and their distances. This relationship is known as Hubble's law and is expressed by the equation V equals h0 asterisk d, where V is the speed of departure, d is the distance, and h0 is the Hubble constant, which represents the current rate of expansion of the universe. Big Bang theory. The observation of redshift in galaxies was one of the crucial pieces of evidence that corroborated the Big Bang theory. This theory posits that the universe originated in an extremely hot and dense state about 13.8 billion years ago and has been expanding ever since. Metric expansion. The redshift theory and expansion of the universe is based on the Friedmann-Lemaitre-Robertson-Walker metric, FLRW, which describes the geometry and dynamics of the expanding universe. It includes parameters such as matter density, dark energy density, and expansion rate. Event horizon and observable universe. The expansion of the universe implies that parts of space are moving out of the range of observation, creating an event horizon. The region we can observe is known as the observable universe, and galaxies beyond that limit are moving away from us at speeds greater than the speed of light, due to the expansion of space. The theory of redshift and expansion of the universe not only provides an explanation for the apparent darkness of the universe, but also has profound implications for our understanding of the history, evolution, and fate of the cosmos. It has played a crucial role in the foundation of modern cosmology and continues to be an active area of research and exploration, helping to answer questions about the fundamental nature of spacetime and the dark energy that drives the accelerating expansion of the universe. Cosmic dark age theory. While this is not an established scientific theory, it is an idea that scientists discuss within the context of the evolution of the universe. The cosmic dark ages is a hypothetical phase in the history of the universe that would have occurred a few million years after the Big Bang. During this phase, it is believed that the universe was filled with hydrogen and helium, but there was not yet a significant formation of bright stars and galaxies. This would lead to a lack of visible and ultraviolet light sources in the cosmos, resulting in a relatively dark period in terms of detectable electromagnetic radiation. The theory suggests that as the universe continued to evolve, gravity began to act on the small density fluctuations present in the early universe. This eventually led to the formation of the first stars and galaxies, which began emitting ionizing radiation capable of illuminating intergalactic space. This process is known as reionization, which marks the end of the cosmic dark ages. It is noteworthy that the cosmic dark age is a theoretical concept and has not yet been confirmed by direct observations. However, scientists are actively seeking evidence of this period through observations of distant galaxies and studies of the properties of the cosmic microwave background. Dark matter theory. Dark matter is a form of matter that does not emit light or radiation and is therefore invisible. However, Its gravitational influence is evident through the effects it exerts on galaxies and star clusters. The significant presence of dark matter in the universe may contribute to the apparent darkness, as this matter does not emit detectable light. The dark matter theory is a central concept in cosmology and particle physics, developed to explain phenomena observed in the universe that cannot be explained by the visible matter, baryons, we know alone. This theory suggests the existence of a form of matter that does not emit light or other traditional forms of electromagnetic radiation, making it invisible and therefore difficult to detect directly. Here are the key points of the dark matter theory. Observational evidence, astronomical and cosmological observations have shown that the amount of visible matter, stars, planets, galaxies, etc., is insufficient to explain the gravity observed on galactic and cosmological scales. For example, the velocity of stars at the edges of spiral galaxies is greater than what would be predicted by visible matter alone. This discrepancy is known as the rotation curve problem. Gravity and gravitational effects. The theory posits that dark matter is composed of particles that have mass and therefore exert gravity. This extra gravity would be responsible for keeping the galaxies cohesive and explaining the observed rotation curves. In addition, dark matter is also important in the formation and evolution of cosmic structures such as galaxies and galaxy clusters. Unknown composition. The exact nature of dark matter is still a mystery. We don't know which particles make it up. Several candidates have been proposed, including supersymmetric particles, axions, and other hypothetical particles. However, to date, there have been no direct detections of these particles. Detection and experiments. Scientists are conducting experiments in underground labs and using sensitive detectors in hopes of capturing direct evidence of the dark matter particles. In addition, particle accelerators, such as the Large Hadron Collider, LHC, can help better understand the properties of particles that could be components of dark matter. The presence of dark matter is crucial to explaining the formation of cosmic structures as we observe today, including the distribution of galaxies and the cosmic microwave background. Cosmological models that incorporate dark matter are consistent with many observations, including the theory of inflation and the accelerating expansion of the universe. The dark matter theory remains an active area of research and investigation. While there is still much to learn about the nature of dark matter, its existence plays a key role in understanding the structure and evolution of the universe. What about you? What theory do you believe explains the darkness of the universe? Comment in this video on your theory for this mystery. Dark energy theory. Dark energy is a form of hypothetical energy that fills space and is associated with a repulsive force that is accelerating the expansion of the universe. Although not directly responsible for visual darkness, dark energy plays an important role in the evolution and fate of the universe, influencing its structure on a large scale. The dark energy theory is an important concept in modern cosmology and is related to the accelerating expansion behavior of the universe. It was proposed to explain a surprising observation made in recent decades. The rate of expansion of the universe is accelerating, contrary to what was initially expected. Here are the key points of the dark energy theory. Discovery of accelerated expansion. In the 1990s, observations of distant supernovae revealed that the universe was not only expanding, but was also expanding at an ever-increasing rate. This was a surprising discovery, as it was believed that gravity should slow the expansion. Dark energy. The theory of dark energy postulates the existence of a form of energy that fills space and exerts a negative pressure, counteracting the gravitational attraction of the masses. This exotic energy is called dark energy. It is different from dark matter, which is a form of matter that does not emit light. Cosmic acceleration. The presence of dark energy in the universe would explain the accelerated expansion, as its negative pressure would act as a repulsive force, counterbalancing the gravitational pull of normal masses, matter and radiation, and accelerating the expansion of the universe. Cosmological constant. One of the ways to represent dark energy is through the cosmological constant, denoted by lambda. It was introduced by Albert Einstein in his equation of general relativity, but then he abandoned it when the expansion of the universe was discovered. However, the cosmological constant was resumed with the discovery of accelerated expansion, as it could represent dark energy. Unknown nature. The exact nature of dark energy is still a mystery. It could be a fundamental feature of empty space, a form of energy field, or even a property of hypothetical particles. To date, it has not been possible to directly identify or detect dark energy, making it one of the greatest enigmas of modern cosmology. Impact on cosmology. Dark energy has profound implications for the future evolution of the universe. If its influence continues to increase, the universe could eventually expand so rapidly that distant galaxies will become inaccessible. However, its total effect depends on its exact amount and how it interacts with other forms of energy and matter. The dark energy theory is an active field of research, with scientists conducting detailed observations and experiments to better understand its nature and its impact on the universe. It plays a crucial role in building cosmological models that explain the evolution of the universe from the Big Bang to the present day. Inactive galaxies and dead stars theory. As the universe ages, some galaxies deplete their supply of gas for star formation, leading to stellar inactivity. This results in fewer bright and luminous stars in the universe. In addition, many stars eventually burn out and become white dwarfs or black holes, which do not emit visible light. The theory of inactive galaxies and dead stars is related to the evolution of galaxies and stars over cosmic time. This theory explores what happens to galaxies and stars when they cease star formation and enter a phase of inactivity. Here are the main points related to this theory. Formation and evolution of galaxies. Galaxies form from the agglomeration of matter, including gas, dust, and dark matter. Through gravitational collapse processes, they can contain billions or trillions of stars, as well as other components such as supermassive black holes and star clusters. Over time, galaxies interact with each other, merge, and evolve. Stars and stellar life cycle. Stars are born from clouds of gas and dust. Throughout their lives, they go through several phases, such as the main sequence, where they spend most of their lives converting hydrogen into helium through nuclear reactions, red giant, supernova, and others. Eventually, stars can become dead stars, such as white dwarfs, neutron stars, or black holes, depending on their original mass. Active versus inactive galaxies. Inactive galaxies are those that have stopped forming stars in a significant way. This can occur for a variety of reasons, including the exhaustion of the gas needed for star formation, galactic interactions, or other external influences. On the other hand, active galaxies continue to form new stars and often harbor active galactic nuclei, where supermassive black holes emit intense radiation. Dead stars and remnants. As stars deplete their nuclear fuel, they can turn into stellar remnants. A star of low or medium mass, for example, can become a white dwarf after exhaustion of its fuel. More massive stars can explode into supernovae and leave behind black holes or neutron stars. Contribution to the universe. Inactive galaxies and dead stars play an important role in the long-term evolution of the universe. They contribute to the so-called stellar age, where the formation of new stars gradually decreases and more evolved and remnant stars accumulate. Observations and studies. Astronomers study inactive galaxies and dead stars through observations at different wavelengths, such as visible light, infrared, radio, and X-rays. These observations help to understand the physical properties of these objects, such as chemical composition, mass, and age. The theory of inactive galaxies and dead stars is an important part of cosmology and astrophysics, providing insights into the evolution of cosmic structures and star systems over billions of years. Observational limitations theory. The theory of observational limitations is not a widely recognized scientific term, but I can address the concept of observational limitations in science in general. Observational limitations refer to the constraints and challenges that scientists face when trying to collect data, perform observations, and make measurements in their research. These limitations can arise from multiple sources and can impact the results, interpretations, and conclusions of a study. Here are some of the key areas where observational limitations can occur. Instrumentation. The quality and sensitivity of observing instruments can directly affect the accuracy of measurements. Sometimes scientists do not have access to advanced instruments or cannot use specific techniques due to technological limitations. Resolution. The ability to distinguish details in an observation may be limited by the resolution of the instruments. The lower the resolution, the fewer details can be identified. Environment and conditions, atmospheric conditions, weather, light pollution, and other environmental factors can affect the quality of observations, especially in astronomy and ground-based observations. Time and duration. Some observations require prolonged periods of time to detect subtle changes or rare events. Time constraints can prevent you from getting a complete set of data. Distance and accessibility. In areas such as astronomy, distance limitations can make it difficult to obtain detailed observations of distant objects. In addition, some regions may be inaccessible for observations, as in the case of extreme environments or microscopic objects. Sampling and bias. When collecting data, selecting a sample can introduce bias into the results, making them unrepresentative of the larger population. Interference. In some situations, the observation itself can affect the object or phenomenon being studied, changing its natural behavior. Intrinsic nature of the phenomenon. Some natural phenomena can be intrinsically difficult to observe due to their properties or lack of means to detect them. Theoretical limits. Some observational limitations may be related to fundamental principles of physics or to our current understanding of the universe. Dealing with observational limitations is a critical part of scientific research. Scientists often develop strategies to mitigate these limitations, use statistical methods to deal with uncertainties, and sometimes collaborate with experts in different fields to obtain more comprehensive and accurate observations. Sachs-Wolf effect theory. The Sachs-Wolf effect theory is a physical explanation for temperature fluctuations in the cosmic microwave background, CMB. This theory was proposed by Rainer Sachs and Arthur M. Wolf in 1967. The Sachs-Wolf effect suggests that the temperature fluctuations observed in the CMB are influenced by the variation in the geometry of spacetime as light travels from the moment of the last scattering, when the radiation was released, about 380,000 years after the Big Bang, to reaching our detectors on Earth. The density fluctuations that existed at that initial moment left a signature in the CMB, causing temperature variations when radiation travels through regions of different gravitational densities. The cosmic microwave background, CMB, is the remnant of the Big Bang and is considered one of the most solid evidences of the Big Bang theory. It is an electromagnetic radiation that fills all observable space and is almost uniform in temperature, with small temperature fluctuations on very small scales. The CMB is believed to be a photograph of the universe when it was only about 380,000 years old, making it one of the oldest forms of light we can detect. This radiation was emitted when the universe became transparent, allowing light to travel freely. Temperature fluctuations in the CMB, observed on missions such as the COBE satellite, WMAP, and Planck, provided crucial information about the initial distribution of matter in the early universe. They reveal slightly denser, hot regions and slightly less dense, cold regions, which later gave rise to the structures we see today, such as galaxies and galaxy clusters. The Sachs-Wolf effect is one of the main contributions to the understanding of the observed fluctuations in the CMB and how they relate to the properties of the universe in its early phases. Both of these concepts are deeply rooted in cosmology and are fundamental to our understanding of the history and evolution of the universe, from its earliest moments to the current state of cosmic structures. Theory of black holes and exotic matter. The presence of black holes, which are regions of space where gravity is so intense that nothing can escape from it, can contribute to the darkness of the universe. They absorb light and other forms of radiation and do not emit any light by themselves. In addition, the existence of exotic forms of matter, such as dark matter, not to be confused with dark matter, may also play a role in cosmic darkness. These forms of matter have unique properties that could influence the emission and absorption of light on cosmological scales. Black hole theory is a fundamental part of theoretical physics and astrophysics. While exotic matter can refer to various hypotheses about forms of matter beyond known types, I will briefly explain these two concepts. There are different types of black holes, based on their masses. Stellar black holes, they form from the gravitational collapse of massive stars at the end of their lives. They have masses several times greater than that of the Sun. Supermassive black holes, found at the center of many galaxies. These black holes have masses millions or billions of times greater than that of the Sun. They are believed to play an important role in the evolution of galaxies. Intermediate mass black holes, these are hypothetical and would be in a mass range between stellar and supermassive black holes. Black holes have profound effects on the structure of spacetime around them, affecting the motion of nearby objects. Although we can't directly see a black hole, as its gravitational pull is so strong that not even light can escape, its presence can be inferred by the behavior of neighboring objects. Exotic matter. The term exotic matter refers to hypothetical forms of matter that are not composed of the normal baryons, protons, neutrons, and electrons that make up atoms. It is discussed in various areas of theoretical physics, such as cosmology and particle physics, to explain observed phenomena that cannot be explained by ordinary matter. Some examples of exotic matter include dark matter, a form of non-luminous matter that exerts gravitational influence but does not emit light. It is believed to account for much of the mass of the universe and is crucial for the formation of cosmic structures. Free quarks. Normally, quarks are confined within hadrons, particles composed of such as protons and neutrons, but some theories suggest that quarks may exist as free particles. Axions, hypothetical particles that could solve some questions in particle physics and cosmology, including the problem of CP violation, a discrepancy between particle and antiparticle behavior. Strange matter, a form of matter in which strange quarks, one of the types of quarks, are free and not confined within hadrons. This form of matter could be stable and denser than ordinary matter. Remember that exotic matter is largely speculative and its existence has not yet been confirmed experimentally. These ideas are explored in theories to explain phenomena not yet understood by conventional physics. Theory of gravitational shift of light and gravitational lensing. Einstein's theory of relativity predicts that light can be deflected when it passes through intense gravitational fields, a phenomenon known as gravitational lensing. This can distort the trajectory of light from distant galaxies, causing their light to be deflected or magnified, while gravitational lensing can allow us to see galaxies that would otherwise be invisible. They can also contribute to an overall darker appearance of the universe, since light can be scattered and distorted. The theory of gravitational deviation of light and gravitational lensing are fascinating concepts that explore the influence of gravity on the trajectory of light and how this can lead to interesting observational phenomena. I'll explain both concepts. Theory of gravitational deviation of light. The theory of gravitational shift of light is a direct consequence of Albert Einstein's theory of general relativity. According to this theory, gravity is not just a force acting between masses, as described by Newtonian gravity, but is a curvature of spacetime itself around masses and energies. This means that massive objects can bend the spacetime around them, causing the trajectory of light passing through this region to be deflected. A classic example of this deviation is the deflection of starlight as it passes close to the sun. This phenomenon is observed during a total solar eclipse, when stars near the sun appear slightly offset from their normal positions in the sky. This effect, known as the gravitational shift of light, was confirmed experimentally in 1919 during an expedition led by Arthur Eddington to observe a solar eclipse. Gravitational lenses. Gravitational lensing is a phenomenon that occurs when light from a distant source is bent and focused by a massive object intermediate between the light source and the observer. This curvature can create multiple images, arcs, or rings of light around the massive object. There are two main types of gravitational lensing. Strong gravitational lenses. In this case, the curvature of spacetime is so sharp that multiple, separate, and highly distorted images of the original light source form. Sometimes multiple images of the same distant galaxy can be seen around a massive object, such as a galaxy cluster. Weak gravitational lensing. In this case, the deviation is more subtle and does not create multiple distinct images, but causes a tangential distortion in the images of background galaxies. Gravitational lensing provides a powerful tool for studying extremely distant and faint objects that would not normally be directly detectable. In addition, they have implications for determining the distribution of dark matter in galaxies and galaxy clusters, since dark matter gravity also bends light. In summary, the theory of gravitational shift of light and gravitational lensing are two concepts that illustrate the deep interaction between gravity and light, providing valuable insights into the nature of spacetime and the distribution of matter in the universe. Modified steady-state theory. This theory is a variation of the original steady-state theory in cosmology. The steady-state theory was originally proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948 as an alternative to the Big Bang model. While the original steady-state theory was largely discarded due to observational evidence in favor of the Big Bang model, modified variants have been proposed over the years. The original steady-state theory held that the universe did not have a singular beginning in time, but rather continuously created matter to maintain a constant density while expanding. This theory was controversial and faced observational challenges, such as the discovery of the cosmic microwave background, which is consistent with a hot, dense beginning, namely the Big Bang. The modified variants of the steady-state theory attempted to incorporate some of the ideas of the original theory, but also to address the observational evidence in favor of the Big Bang. However, these modifications have generally not been widely accepted by the scientific community. Remember that currently the predominant theory for explaining the origin and evolution of the universe is the Big Bang model, which is supported by a variety of observational evidence, such as the cosmic microwave background, the abundance of light elements, and the distribution of galaxies in the cosmos. If there were more recent developments or variants of the modified steady-state theory after my knowledge date, September 2021, I would not have updated information on these developments. These theories represent a diverse range of ideas that scientists have explored to understand why the universe looks so dark. Each contributes to the ongoing search for answers about the fundamental nature of the cosmos and the forces and processes that shape its current appearance. What about you? What theory do you believe explains the darkness of the universe? Comment in this video on your theory for this mystery. If you liked this video, leave your like and subscribe to the channel. Also stay on top of all our videos that are full of mysteries and curiosities.